All right, it's a real pleasure to introduce Germano D'Abramo, someone whose research I've been following for about 10 years, but I've never actually met. So Germano is a physicist and has worked as a researcher in various institutes and companies in Rome between 1998 and 2014 on near-Earth asteroid population modeling and deflection. His research activities and interests also include special relativity, classical electrodynamics, and the history of the philosophy of physics. He currently works for the Italian Ministry of Education as a physics teacher. He is the author of the books The Impact Clan in 2015 and Probing the Limits in 2017. Germano, please screen share.
Thank you, Daniel, for the nice introduction. It's a real pleasure for me to be here with you. Let me share my presentation. Hope you can see my presentation and hear me. Oh, sorry. Can you see my presentation?
Yes, your presentation looks good. We can hear you just fine.
Well, what I'm going to present today is the results of my contribution to the challenge to the second law of thermodynamics that I did more than 10 years ago, and for which I want to acknowledge the kind moral support from Daniel Sheehan. Since then, I never come back to this research. So what we will say today is more or less a still picture of 10 years ago. But I believe the results are still interesting and worth telling. Well, what's this all about? Well, I have studied analytically and numerically this simple and well-known idea, exploiting the photoelectric effect of the blackbody radiation on materials with different work functions. Let me remind briefly what a work function is. The work function is roughly the minimum energy required to extract an electron from the bulk of a material to its surface. What you see on the left is a sketch of a capacitor, which I've dubbed thermo-charged capacitor TCC, where two plates, A and B, are housed inside a vacuum vessel, and plate A and part of plate B are made of the same metal with the work function phi2. Plate B is coated with a semiconductor with a much lower work function phi1, and the whole device is at uniform temperature. Both plates, A and B, receive photons from the blackbody radiation, but being phi2, the work function of the coating on plate B, of A, or the electrode A, greater than phi1, the electrons extracted by the photoelectric effect from the coating of B to plate A are more numerous and with a higher kinetic energy than those extracted from plate A to plate B, at least in the early phases of the process. On the right, there is a sketch of the blackbody radiation distribution. This gives the spectral radiance versus the frequency. Well, it roughly tells us the number of photons with a given energy h nu in the thermal radiation at a specific temperature, and it is easy to see why more electrons are extracted from B to A with a higher kinetic energy. All that means that a net flux of electrons should flow from plate B to plate A, and therefore there should be an unbalanced emission from B to A. Okay, so how do we expect the TCC to work? Well, in the case of an open circuit TCC at equilibrium, like in the image on the left, we expect that after a suitable interval time, an equilibrium potential difference, delta V, is established across the plates. At equilibrium, delta V is necessarily equal to phi2 minus phi1 divided by the electron charge. Because only with that value, the energy needed by an electron to get extracted from the coating of plate B and reach plate A becomes equal to the energy needed by an electron to get extracted from plate A and reach plate B. Only in this case, there will be no more imbalance in the two fluxes of electrons. Well, in the case of a short circuit TCC on the right, a current I should flow across the circuit, and if the resistance of the circuit external to the TCC is negligible, that current should be equal to the thermionic current across the plates. Now, before getting to the mathematical and numerical simulation of a TCC, let me dwell on two objections that could be advanced. I must warn you that this part, the next two slides, are a bit involved, but I try to keep it as simple and short as possible. It is important to reply to these objections because if they were correct, the TCC will not work as expected. And to better introduce them, these two objections, let me switch to a topological analog of the short circuit TCC on the left. And it is this horseshoe-shaped thing on the right. The right half of the horseshoe represents plate A, part of plate B and the connecting wire, these things. And all this stuff has work function equal to phi2. The left half is the coating of plate B, and it has a work function equal to phi1. In both images, J2 indicates the vacuum gap between the plates. Well, it is known that when two materials with different work functions, in particular a metal and an N-type semiconductor, like in our case, are physically joined, a potential difference, delta V, builds up across the contact junction J1. This potential is called contact potential, and it is generated by the electrons that are pushed from phi2 materials, the yellowish one, to phi2 materials across the J1 by thermally driven diffusion forces. A higher amount of electrons move from left to right rather than the other way around, simply because it's easier to pull electrons out of a lower work function material. The diffusion process lasts until a dynamical equilibrium is reached between the diffusion forces that push electrons to the right and the electric force to the built-in electric field across J1. Also in this case, the contact potential delta V is equal to phi2 minus V1 divided by the electron charge. And the reason is the same as in the previous slide for the final equilibrium of the thermionic charging process. And the built-in electric field across J1 is roughly equal to the contact potential divided by the width of the depletion region, XD, namely the thin layer across J1 where the diffusion of electrons has taken place. Well, it is also a widely held belief that as soon as one joins the two halves at J1, a potential difference equal and opposite to the contact potential here at J1 should instantaneously build up also across the gap J2. Notice that this potential, the delta V across J2, across the gap, is not deriving from the thermionic charging process, It is intended to be instantaneously generated by the movement of electrons in the bulk of the horseshoe, just after the physical contact of the materials at J1. Well, people expect the potential difference across J2, across the gap, because of an allegedly straightforward application of the Kirchhoff loop rule. Well, what is the problem with that? Well, if the potential difference were really there across the gap, then the thermionic charging process across J2 could not even start. Since the delta V across J2 is equal to Phi2 minus Phi1, okay, divided by the electron charge, no net electron flux from plate B to plate A could be possible from the outset. As I have described before, the energy required for an electron to get extracted from from one plate to reach the other will be the same in this case, and incidentally equal to Phi2. Therefore, there would be no net displacement of electrons across the gap J2, and therefore there would be no current in the short circuit TCC on the left. Moreover, and this is objection 2, even if a net flux of electrons were possible across the gap, still the current will not flow across the whole circuit. In fact, J1 is a metal N-type semiconductor junction, also known as Schottky junction, and it is known to have a rectifying properties. Okay, under biasing, electrons easily flow from the semiconductor to the metal, from left to right across J1, but not that easily from the other way around, from right to left across J1. Okay, let me give a short reply to objection 1. Well, my stand is that there is no instantaneous potential difference across the gap J2 caused by the physical joining of the materials, of the two materials at J1. To prove that, I apply the basic definition of potential difference. The potential difference between 2 points A and B is defined as minus, minus the work done by the forces acting upon an electron that moves all along the path gamma, joining A and B, divided by the electron charge. I do this calculation along the blue line on the right, in the bulk of the horseshoe across J1. Here, F int stands for all the forces acting upon the test electron when it moves across the path gamma. From equilibrium consideration, it is clear that F int, the sum of the two forces, or all the forces acting upon the test electron, can be different from 0 only across the junction J1. When the text electron crosses J1, it does feel only two kinds of forces: the diffusion forces pushing to the right, and the electric force due to the built-in electric field pushing to the left. By the way, the test electron does feel the diffusion forces exactly like all the electrons in the depletion region around J1. Okay, since the diffusion forces dynamically sustain the electric field at J1, by the way, if I switch it off the diffusion forces at J1, the built-in electric field will go to 0. So since the diffusion forces dynamically sustain the electric field at J1, these two forces, the electric forces and the diffusion forces, must always be present across J1, and also must be equal and opposite at equilibrium. Therefore, the total force is equal to 0 on average, and together with the delta V, between any 2 points A and B in the bulk of this horseshoe-shaped thing. All that means that physically joining different materials at J1 cannot instantaneously cause any potential drop across the gap that will kill the thermionic process from the outset. Okay, let's face objection 2. We know that every Schottky junction is characterized by a reverse leakage current that overcomes the rectifying barrier. And that current may be high or low depending upon several factors. For instance, according to the literature, it may range from 10 to the minus 8 to 10 to the minus 2 amps per square centimeter. The reverse leakage current obviously depends upon the reverse bias, but this dependence is quite flat, so to speak. Reverse current doesn't change too much with the reverse bias, at least below the breakdown voltage. But in our device, we are very far from the breakdown voltage. The reverse leakage current also depends upon the material used and the junction preparation. For instance, annealing seems to increase the reverse leakage current. And it also depends upon the temperature. The higher is the temperature, the greater is the reverse current. And also depends upon the width of the depletion region XD. Since the thinner is the region, the greater is the reverse current due to the tunneling effect. So we see that even under a small bias, a non-zero current can cross the junction even in the wrong direction, so to speak. Okay, we finally come to my numerical simulation and results. I mathematically modeled a spherical TCC. For the low work function coating, I have chosen the silver cesium oxide photocathode. It is a well-known photocathode material, and it is known in the literature to have a work function of nearly 0.7 electron volts or 0.8 electron volts. The inner and the outer spheres are made of metal with a work function equal to 4 electron volts. The modeled TCC is 40 centimeter wide, and as you may see, the ratio between the outer and the inner radius is taken to be equal to 2, because it can be proven that this choice maximizes the charging speed for an open circuit TCC. But the charging speed is not a crucial feature here. What's important is the power output of a short circuit TCC. We show you in a moment. Another important parameter is for the simulation is the quantum efficiency of the materials. Quantum efficiency is roughly the ratio between the number of electrons extracted by the radiation and the number of photons impinging on the material, on the surface of the plates. And it is clearly a frequency-dependent parameter, and I have plugged in the equation only mean values over frequency. I have used quite conservative values for eta 1 and eta 2. According to the literature, a more realistic value for eta 1 for the quantum efficiency of the silver cesium oxide coating will be 10 to the minus 3. And eta 2 equal to 1 is surely not realistic. I am sure that that does not exist any material with the quantum efficiency equal to 1. Well, sorry. Well, my interest at the time of the simulation was to explore the worst case scenario and to see if I could get something different from 0. And it seems to be the case, as I show you in a moment. Okay. This graph shows the charging profile of an open circuit TCC. As you may see, even with the previous very conservative values for quantum efficiency, it is expected to reach a voltage of nearly 0.3 volts in less than 2 hours, more or less. With more realistic values for the quantum efficiencies, the same voltage is probably reached in a few minutes. And here you may see, for the sake of completeness, the differential equation that governs the charging process. Okay, now let's see the more interesting case of a short circuit DCC. The graph shows the power output per unit area of the inner sphere versus the steady state voltage across the DCC and the resistor R. By tuning the value of the external resistance R, we can maximize the power output. The maximum is obtained at 0.03 volts across the resistance of the order of 10 to the 10 ohms. The value of the power output of this model at DCC is of the order of 10 to the minus 14 watts. This value may appear, and in fact is a bit disappointing. And the current design surely has no hope to have an immediate application to the real world. However, as I said before, the main goal of this work was to prove the theoretical validity of the basic idea. You know, I believe that if we can experimentally and unambiguously confirm the functioning of this design, we would have an incentive to study and work on a more efficient design. Okay, let me finish my presentation with some basic and I'm sure unsurprising prescription for a future experimental test of this design. In order to be sure that the TCC works as expected, we need to cut every external disturbance, like for instance man-made and natural electromagnetic fields, natural radioactivity and cosmic particles and so on. And I am pretty confident that this could be done with proper shielding. We must also avoid any non-uniformity of the ambient temperature around the device and the measuring instruments in order to prevent any thermoelectric effect. And also a prescription peculiar to this case may be that of placing side by side two TCCs identical in every respect, exception made for the fact that one does not have the lower function coating. You know, that prescription should allow discriminating between the real contribution of the thermionic emission and the background noise. Finally, just a few words on the measuring equipment. As we have seen in the previous slide, the magnitude of the resistance in the short circuit DCC must be very high to have a measurable volt across the device. And so in order to detect something different from zero, we will need an ultra-high input impedance electrometer. And I know that on the market is available this one, Catley 6514, that has an ultra-high input impedance of the order of 1 tera ohm. Okay, here you may see some selected references to my work on the TCC, and I am finished. Thank you very much for the attention.
Wonderful. Thank you, Germano. Okay, you ended, excuse me, you ended quite early, so we have a great deal of time for questions.
Okay.
So let's see who is Dr. Solomon. would you like to start with questions?
Yes, my hand, however, went up for the last lecture,
I
and so
see.
I apologize. But I think I have an important point perhaps to contribute to the last lecture,
Okay,
if that would be possible.
sure.
When you're talking about Kirchhoff's laws, you're in this funny domain between the EE who dropped out of physics because he couldn't handle the math, and the physicist. I'm only being very humorous about it. But at any rate, but I am serious in that when you're at a circuit Kirchhoff level, all of a sudden a bunch of physics tends to drop away and it's not considered. And in our work at the Intelligy Institute, we love this capacitor problem. I thought the presentation was incredible, and I think it's going to lead to a lot of important things. At any rate, let me get to the point, and that is that when you're doing Kirchhoff's law, you got to realize you're dealing with it across the resistor or any element. You have a voltage drop. And as soon as you have a change in voltage, you have an electric field. So now we got to remember, oh, gee, electric field, we really can't talk about, we got to talk about the electrons, right? The electrons, and therefore they're accelerating faster as they go through the electric field. They're not all at the same speed. And some of them can get quite fast. Then, of course, you've got the flow of like the Newton pendulums hitting one another, that kind of a group velocity versus the actual phase velocity versus group velocity. And then you get a whole bunch of other electromagnetic effects. And then, of course, by now, you know, I'm a time-space guy. And so therefore, I'm always thinking not of photons, but of a photon is nothing more than an accelerated charge communicating to another accelerated charge. So all I'm saying is that I think if those elements can be brought into this, namely the electric field, the I don't believe in fields, but the electric field, but mainly the effect of accelerated charges to accelerated charges, we might, and of course, this is everything you're talking about in thermal is nothing more than accelerated charges talking to accelerated charges. If you can start to think at that model level, you're now at a commonality where this unuseful energy is the same as the so-called useful energy. It just has a different time-space nature to it, and the way in which these accelerated charges, which we're calling photons, communicate from one charged particle to another. So getting back to it, Kirchhoff laws involves fields because the voltage changes. It causes, therefore, a different speed of the electrons traveling through these circuits. They're not traveling at the same speed. And I would love to see this consideration brought into this wonderful work and see what comes out.
Germano, would you like to comment?
Okay, yes. Thank you for the questions. Well, I agree with you that my analysis that you may see now on the screen is probably too simple. Okay, and I agree with you that we need to put into consideration other factors that may have an effect on the final results of the calculation. This calculation, okay, and for this reason, I myself, I am the first person who, in fact, do not believe too much to this calculation, to these results, which are mainly theoretical results. Okay, so what I want to stress is try to physically implement and check experimentally this design in order to see, taking all the prescription I said before in the last the penultimate slide, in order to be sure that this device works as expected. Okay, I agree with Robert that using only the Kirchhoff law and neglecting some factors that maybe must be taken into account, okay, in the calculation of the Kirchhoff law could change the picture. And this is the reason why I just presented this simple analysis and simulation, numerical simulation, but my goal, my target, my future target is to try to actually check experimentally, okay, this design.
Thank you. Thank you very much for your response. But this was also primarily to Paul Thibodeau, and if he's online, I would like to get a response.
Yes, I am here. Yeah, thanks for those comments. I think you're right. I think a lot of what we've done really, I think was first done kind of in the optics community, where they really looked at noise and the different effects that can happen there. And actually Surendra Singh, who's part of our group, is kind of skilled in that art. And so, basically I agree with you. And I think that I think that field probably can get to do more fundamental look at these things. Thank you.
Okay.
Thank
Thank
you. I'd like to call on David Miller. David? David, are you there? Okay. I think David. Okay, well, what I'd like to do then is just kind of waiting for David to get on. I'll exert the privilege of the chair. Germano, I have a couple of questions concerning your talk. First of all, the steady state voltage that you're claiming, it looks like it's around 30 millivolts, and that's roughly the thermal voltage that you'd expect setting KT equals to QV. Is that coincidence, or is there deeper meaning there?
Well, I believe that well, I don't know if there is if it is a coincidence, but I guess it is not, because I used a very complex differential equation to model the charging process. Okay. But I am sure that inside the machinery of the mathematics of this differential equation, it is always present KT. So I believe that it is not a coincidence.
Okay. Okay, good, thank you. And also I'd like to just, if you could bring your talk back, I'd like, if you could go to page 5.
Okay.
Yeah. Just please share that again, because I have another fundamental question.
Okay.
Okay.
This one? Yeah,
that's good. Okay, so you have a horseshoe here, which looks very much like an upside down version of the horseshoes that we're using in solid state versions of challenges. And the junction 1 that you have here would be the depletion region, yeah, between two semiconductors and the J2 gap. But you're correct that when you first join these junctions, that in the upper junction J2, you don't immediately get charges, but in the end you have to. And that's demanded by Faraday's law, or conservation of energy, Kirchhoff's law, in other words. If you wish, if you take an integral around a closed loop, the electric field, net electric field around a closed loop line integral has to be 0. So if you have an electric field here, you have to have an electric field somewhere else in the system. It can't be in the bulk because that would drive a current. Therefore, it has to be across the gap. So straight Maxwell's equations demands that in steady state, you have to have charges here on the gap. You have to have an electric field here. But more than that, that electric field has been measured by multiple groups around the world. I've built these junction gaps in semiconductors, and multiple independent groups have measured the electric field. So in fact, there is an electric field here, and that's experimentally determined and analytically required if you believe Maxwell's equations. Okay. So I don't know how you want to respond. If you can respond to that, I'd appreciate it.
Well, yes. What I have shown here is half of the application of Kirchhoff law. I made this calculation only from point A and point B inside in the bulk of the horseshoe. We can extend this integral to become a circular integral, a closed integral. Sure. Okay. And but I think that what I have shown here, the fact that the work done by all the forces acting upon the text electron across J1 is still the same, also in the case of a circular closed integrals. Okay, and if you perform a closed integral, you should, according, this is my position. Okay, should be also equal to 0, because you see, it is equal to 0, the whole work, the overall work done by all the forces across J1. Okay, and because in the balance of the integral, I also included not only the electric force due to the built-in electric field across J1, but also the diffusion forces that must be always there, must be always present, and the forces, the diffusion forces, should be equal and opposite to the electric field across J1, because if one could switch off these diffusion forces, the built-in electric field will go to 0 immediately. Okay.
Yeah. A couple of, yeah.
I agree with you that the electric field has been measured, experimentally measured across the gap.
Yeah.
I'm now thinking of the use of a Kelvin probe system to measure this field, probably.
Right. Well, the Kelvin probes were used to measure that J2 electric field. The thing is, though, is in terms of the forces in the lower gap, J1. Okay. You have, I mean, the electric field that builds up there in the first place is due to diffusion, cross diffusion of charges, at least in the semiconductor case. And in terms of diffusion forces, if you're talking about Brownian motion, that average force is 0, and you have to do a time average of it, which will give you 0 there. So that needs to be, this has to be done delicately, this internal force. So I think you'll find the average diffusive force is either 0, the way if I'm understanding it correctly, or else it's being double counted, because the electric field of the built-in electric field is the result of cross diffusion in the first place.
Okay.
Isn't diffusion force necessarily transient? Because, you know, electrons move from one side to the other, and then you have a counter potential that cancels out the initial potential difference. So then at like long times, you'd expect no diffusion force?
Well, yeah, I'm just I'm fuzzy on what the diffusion force is here. The built-in potential, at least when it comes to semiconductors, I'm not talking about metals here, but semiconductors, is the result of diffusion in the first place.
All right.
You're trading you're trading chemical potential difference for electrostatic potential difference there.
Sure.
So if you're throwing in another diffusion force, that would be a fluctuating force, which has a time average of 0, as you're saying. I believe that's correct.
Yeah.
So, anyway, it's an interesting proposal, and I think, the measurement should be made.
Yeah, definitely. Yeah.
For the metals. Yeah. So other questions? David, are you back? Sorry. Hands up. Garrett, I think you were. Yeah. You had your hands up too.
Dan, David put his question in the chat because his mic isn't working. He says, can Germano please address how much current would go up with increased temperature?
Okay, thank you.
Okay. Well, I have in the simulation I have done. I used also. I made the calculation also for two further different temperature, 300 Kelvin to 296 Kelvin, in order to give an idea, an hint of how this, in this case, the voltage across the open circuit DCC change with temperature. And well, I didn't do the calculation about the current, and well, I don't know, but I don't know how the dependence of the current is with temperature. I should redo the calculation in order to see how the current across the short circuit DCC change with the temperature. But I believe that the trend is similar to this factor multiplying this equation. Okay, so it should scale with the third power of temperature.
Mm-hmm. Okay, good. Other questions? Garrett, did you have a question?
Yes. So you talk about power, but then you also mentioned needing to use a very high impedance voltmeter to measure this, and Kelvin probe, another example. I like to think of two types of second law violations, the drastic kind, but also a soft violation. And so for me, a soft violation would be where you produce a potential difference, but you're not actually getting work out of it. And I wonder, is this perhaps a soft violation in which you're distorting something, but it's not clear that we could get substantial continuous work?
Okay. Well, I believe that with the short circuit DCC, a steady current should flow across the resistor R. So even if it is a teeny power output, it should be a continuous electrical power output. And this is how I see this, the behavior of this DCC. These two spheres subtract thermal energy from the ambient heat and transform this thermal energy in current that pass across the resistor. So I believe that it is. I think that if this design works, probably it works violating in a strong way the second law of thermodynamics. This is my idea. But the problem with this design is, as you may see, is the very tiny power output that is too close to the background noise to be detected and unambiguously detected.
It's an interesting issue how much power can really be obtained, or if nature is kind of limiting this to these small numbers. For example, even with Paul Thibodeau's earlier calculation about getting power out from a diode and Daniel's epicatalysis and so on, is there some limit that nature has to nonlinearity that ends up saying, yeah, you can violate this, but just very softly?
Yeah.
I guess the soft and hard violation, I think, is I'm wondering whether that's somewhat of a red herring, in the sense that there's more than one way to skin a cat. I mean, if it may look more difficult if you throw a resistor in, and then you probably should consider thermal noise then, Nyquist or Johnson noise to compete here. But on the other hand, if you go again back to that slide 5, there are other ways of extracting that energy. And there have been propositions in the semiconductor case of using the gap to electric fields to drive electromechanical devices. And detailed numerical simulations indicate that that's feasible. And so what may look like a soft violation in some light, if you cast it in a different light, a different kind of work extraction, the soft violation becomes hard.
I also think 0 is just the most fundamental limit on work extraction. So if you can extract anything, it seems at this point it's no longer a fundamental physics problem. It's just a matter of engineering. I think history shows that we started with all these small effects over and over in physics, but with enough kind of money being thrown at a problem, we have these drastic increases.
Right.
The future's kind of boundless once you get over that initial violation.
Sure. Yeah, so like for instance, some of the more recent epicatalysis experiments with David Miller here at USD, those are putting out milliwatts now. That's not, I mean, it's not large, but it's more than picowatts, and milliwatts are easily measurable. So,
classical. It's no longer a quantum fluctuation.
No, these are not fluctuations.
Yeah.
Okay, other questions? I'm having a hard time seeing everyone's hand here, so if you have a question, please just jump in and we'll sort it out.
Okay, I have a question to Paul Thibodeau, actually.
Who is this?
My question is 2 questions or 3 questions even. First question, how high is the voltage of this battery?
Hey.
Okay,
Did you want to do this?
okay, hold on a second.
Use this time this
but-
way, Daniel. Sorry.
Yeah. So let's
feel a
have
little-
some order here. Hold on a second, Paul.
So,
Are there any questions? Any further questions for Germano D'Abramo? Going
Okay.
once? Okay, then please, sir, go ahead.
Okay, yeah, thanks. I'm not sure I quite followed the question. So the graphene, the small capacitor, has an average voltage of 0, but it does have large voltage fluctuations. And if you make that capacitance smaller and smaller, then the voltage fluctuations rise. This is kind of a well-known phenomenon. In fact, you see it in the semiconductor industry. If you make these chips and you make really small capacitors on these chips, you have to be aware of the large voltage noise that gets generated by them.
So, I mean, the extra energy in the circuit comes from the fluctuations of the graphene layer, isn't it?
Okay, so yeah, sorry. So
because as
well,
I looked at this at your presentation at the very beginning, you told that the fluctuations of the graphene would change the capacity of the capacitor, so that the electrons would be drawn from this battery in one or another direction, depending on the direction, right? And actually, this would be drawing the electron from the battery and transporting it to the capacitor.
oh,
right?
okay, yeah, great. Okay, yeah, I'm with you now. So that's more in the deterministic case. We've done an extremely detailed analysis of the deterministic case. And that battery, if you imagine replacing that battery with a capacitor, it's easier to visualize. Then a little bit of charge comes off on the forward direction, and then a little bit of charge goes back onto the capacitor in the reverse direction. And if it's a lossless, if it's a very low loss system, then you won't lose any of that charge over time. And so in a detailed analysis, and this includes not only from physics, but from kind of the state of the art in engineering circuit analysis, that battery contributes none of the power. In fact, it's whatever's turning the capacitor. If you think of a windmill, it's whatever's turning the windmill. That's the origin of power. It's not the voltage that's present in the system, or in that case, maybe a magnetic field that's present in the system. The power isn't coming from that. It's coming from whatever's turning that windmill, or in this case, the capacitor.
Okay.
But you need, if this battery is accumulator and not a common normal battery, and you want to use this charge, you need an initial charge in this accumulator to make it move through the vibration of the layer, of the graphene layer, isn't it? I'm looking at it as an electronic engineer, as a circuit. There's a circuit, and you have a battery. The battery, if it is more than 0.7 voltage, so it at the first moment when you switch the circuit, the electron comes and charging through the diode D1, the capacitor C1. So
well, yeah, actually, what really happens is the battery charges the graphene capacitor up to the voltage, and it's a small capacitor, so it takes almost no charge to do that. And then the voltage is 0 now. So almost nothing goes into C1. Now, as you rotate it, there's an AC current that's on top of this voltage that's sitting there on the graphene. And it's this AC current which is charging it.
Okay, so this capacitor C0 is graphene is very small, you mean?
Okay.
Well, yes, exactly.
Very
Yes.
small, okay.
Okay, let's wrap it. Let's wrap it. I'd like to redirect back to Germano. Germano, are you still here?
Okay, thank you.
Yeah.
Yeah.
So Germano,
Yeah.
I'd like to address another question, if I may, just to redirect things to this talk. Have you considered the situation when you have a plasma present, which can release space charge considerations for you?
Well, actually, no, I didn't consider the presence of plasma
Okay.
in my design. You are alluding to the space charge between the plates.
Yeah.
Okay.
For instance, yeah. Okay.
No, I didn't take into account this part, but I know that this should be probably included in the numerical simulation, because the presence of the space charge probably changes the equilibrium of an open circuit DCC. But I have not included this the presence of these charges between the plates in the equation, in the charging equation.
Okay. And in terms of power densities, do you have any estimates or feeling for what kind of power densities you could achieve if you had small enough devices? The ones you're proposing may be fairly large, but if you can miniaturize them.
Well, let me share again my presentation, because I want to show you. Well, the last graph, this one, is actually a sort of specific or power, watts per square centimeter, that can be obtained with the previous design that I have shown in my presentation, and also with the equations, not taking into account all the things we have just all the suggestions you gave me. But I do not have much hope to have high power with small devices, because, as you may see, the specific or the power density of this specific design is of the order of 10 to the minus 17. So in order to have a macroscopic production power, we should need not a huge TCC, but moderately small TCC connected together in series or one. Okay. No, I think that this design cannot be miniaturized. Okay.
Okay. Right.
Unfortunately.
Okay. Well, thank you. Are there other questions? Okay. Well, we're coming to the end of the hour, and I believe lunch is next. Is that right, Garrett? Okay. So I think we'll have maybe a few-minute jump on that, but let's thank Dr. D'Abramo again. Thank you for a stimulating talk. Thanks again.
Thank you. Thank you.
Okay.